Good afternoon. Today's webinar is on H-bridge. I'm Dan Baker, President and CEO of NVE Corporation. With me is Pete Eames, our Vice President of Advanced Technology, who will talk about isolators for H-bridges. Here's our agenda. We'll cover the motivation for H-bridges, show an isolated full H-bridge reference design, and go into some details on key components. H-bridges are used to control power to a load in applications such as motor control, power factor control, energy conversion power inverters, battery charging, and hybrid electric vehicles. To show the motivation for H-bridges, let's start with a simple single MOSFET motor driver. It's simple, but you can't reverse the motor and you can't short the motor to drain the back EMF. Adding a second MOSFET to form a half bridge allows the load to be shorted. This circuit requires a P-channel MOSFET, which are less common, and for this circuit the motor voltage must be the same as the logic voltage, which may be impractical. We can add level shifting with an isolator and a DC to DC converter. That allows us to use only N-channel MOSFETs and allows different load, logic, and gate voltages. The ultimate motor driver circuit is an isolated full H-bridge, which allows us to reverse the motor, short the motor for faster stopping, or pulse width modulate to control the motor voltage. We need two DC to DC converters to drive each of the high side MOSFETs. These DC to DC converters are fully regulated and require just two external components, two inexpensive capacitors, and no ferrite beads or other EMI mitigation. This slide shows the detailed reference design. The H-bridge uses 3 isolators for 4 isolation channels. The isolators allow us to drive the high side MOSFETs and level shift the low side MOSFETs from 3.3 to 6 volts. The isolator output impedance is low, about 50 ohms. But we can also add a driver if we need lower impedance or higher gate drive current. We'll show a circuit later. The isolator inputs on each side of the H-bridge are connected in series, which guarantees 2 MOSFETs on the same side won't be on at the same time. That, of course, could cook the MOSFETs. A logic low signal turns on the low side MOSFETs. A high signal drives the high side MOSFETs. Tri-state turns off both the high side and low side MOSFETs. As the high side MOSFETs switch, the isolator power supply and ground change rapidly. This rapid change in voltage can cause current flow across stray capacitance proportional to dV/dt, which causes the isolator to glitch. So common mode transient immunity, or CMTI, is a key figure of merit for H-bridge isolators. Fortunately, these particular isolators have very little stray capacitance, and the devices are symmetrical and well matched, so stray currents tend to cancel. Simple external deglitch circuitry can extend the CMTI to an extraordinary 350 kilovolts per microsecond. This slide shows a circuit from the datasheet. The RC delay filters out pulses less than approximately 10 nanoseconds, and a Schmitt trigger provides a digital output. The isolator coil resistant values shown in the reference circuit are for a 3.3 volt drive, but the resistor values can be changed for 5 volt or other drive voltages. There's a table of recommended values in the datasheet. Also from the IL600 CMTI datasheet, here's a commodity external MOSFET driver if we need lower gate drive impedance, higher gate drive current, or higher gate drive voltage. Here's a picture of a breadboard of the reference circuit. The isolators are the world's smallest and have best-in-class common mode transient immunity. The DC to DC converters are also the smallest devices of their type. Here's a summary of the key components in the reference design. At this point, I'd like to turn it over to Pete Eames to cover the isolators in more detail.
NVE's passive input isolators work by using a micro-scale electronic coil to magnetically excite an ultra-fast spintronic GMR material. Isolator input signals are driven through the coil to create a magnetic field that drives the spintronic resistors configured in a Wheatstone bridge. A high-speed comparator circuit reads the bridge and sets the state of the isolator's output. This is the basis of NVE's patented IsoLoop spintronic technology. All of this is done through NVE's industry-leading polymer ceramic isolation barrier to provide a 2.5 kilovolt rated isolation and virtually unlimited barrier life. The extremely small size of the coil minimizes capacitance. The impedance matching in this configuration is excellent, and the CMTI is best in class.
Thanks, Pete. As far as the specifics, the IL600 series isolators have ultra-high CMTI, extended 3 to 6.6 volt power supply range for direct drive of 6 volt MOSFET gates, full isolation, no input side power supply, and ultraminiature packages. Key ILDC series DC to DC converter specifications are a DFN6 package, that's the world's smallest isolated DC to DC converter, various output voltages. We use the 6 volt version in this demo, soft start so the controller can start before the high side is energized, fully isolated, and the full industrial temperature range. We have several videos demonstrating H-bridges or some of their key components. Any questions? Some questions we've been asked: will these isolators drive silicon carbide or gallium nitride MOSFETs? And the answer is yes, although you might want a driver depending on the gate capacitance and required speed. I showed that circuit earlier from the data sheet. Another question is, can you drive higher gate voltage MOSFETs? So the maximum power supply for our isolators is 6.6 volts, but you can add a level shifting driver. The ICL 7667 driver we showed from the circuit in the IL600 CMTI datasheet operates up to 15 volts. We've focused on 6 volt isolators as there are more MOSFETs in that range, and that process, the lower voltage process, provides superior CMTI. Well, I think that's it for questions. Thanks for attending. Please email or call us if we can help with your H-bridge design.